Hello and welcome. Today we are discussing imaginary numbers, and so I'd like to just kind of do a little review of all numbers first, and then we'll jump into imaginary numbers. So up here I've got what we would consider a Venn diagram, and if you recall, Venn diagrams just kind of identify, a lot of times you have one circle with cat owners and another circle with dog owners, and then where they intersect will be the people that own both. So we've got cat here and dog here, and inside in the middle is those who own both cats and dogs. So this is just kind of an example of a Venn diagram that's pretty basic. Numbered Venn diagram is quite a bit more complicated, a lot more circles, and circles inside of circles. So it's kind of interesting, but we'll get to looking at it real quick here. So the first is the inner circle. The inner circle has the least number of items in it, and that is the natural numbers. And the natural numbers are counting numbers, 1, 2, 3. Not including 0, although in some cases there are mathematicians out there that will include 0 in the natural numbers, but it's nice to just kind of keep them separated, keep the different groups separated, so I like to always not include 0 with the natural numbers. Next we have, in the red circle, are whole numbers. So this circle is bigger than the natural numbers circle. So you might notice the whole number circle is bigger, and that's because it includes all of the natural numbers plus 0. So it's all the counting numbers, 1, 2, 3, 4, 5, all the way to as high as you can count and beyond, but it also includes 0. So that's the whole numbers. I've also got over here a list here. So we've got natural. It looks like the letter N, but it's got an extra line in front of it. The whole numbers also looks like a W, only it has an extra line in front of it. So it's just how mathematicians denote these different sets of numbers, and it's just the symbol for them. Next we've got this. It looks like the letter Z. And it's Z, but that's for integers. Integers is even bigger. Notice the blue circle here. It's even bigger than the red or the green circle, and that's because integers include natural numbers and whole numbers, and also all of the negatives. So all of their negative counterparts. So we could think of it as far negative as you could count. All the way to -3, -2, -1, 0, 1, 2, 3, and then as far as you can count and beyond in the positives as well. So it includes both positive and negative counting numbers, including 0. The next one is a little bit more complicated, and that's the rational numbers. Rational numbers, we use the letter Q for rational numbers. Q is, I don't know why they chose that letter, but that's just the way they did it. I think because R was already taken by the next set. So rational numbers, there's several different ways you can think of a rational number and identify a rational number. The first way that I would think makes the most sense is that if you can take an integer, remember that's a positive or negative counting number, if you can take an integer and divide it by another integer, then you're guaranteed to get a rational number. Any integer divided by another integer will give us a rational number. So that's where the rational numbers come from. So 1 divided by 3 is a rational number. 1/6 is 1 divided by 6. 1/6 is a rational number. 1/9. And we could come up with any number of different ways of writing. We could have 23 over 100. 23 over 100 would be a rational number. 23 over 1,000 would be a rational number. And actually that's what this 0.023 is just another way of writing 23 over 1,000. So that's a rational number. So that's one way of defining rational numbers. We do want to remember that dividing by 0 is undefined. So you can't have 0 in the denominator. So that's the one integer you can't divide by to get a rational number. So we can't have 1 divided by 0. That is not a rational number. The next way you could define a rational number is that it can be written as a fraction. If it can be written as a fraction, then it is a rational. So that's one way some people look at it, as long as the fraction has integers in it. And then the last way is that it could be written as a decimal. Repeating decimal is totally fine, or terminating, so it ends. It has an end to it. It's not a decimal that goes on forever and doesn't repeat. That would then not make it rational. So those are the different ways of looking at a rational number. I think the best way and the simplest method would be to just think of them as numbers that you can write as a integer divided by another integer. The last one in this big circle here, it's the largest circle, and it's the real numbers. Real numbers. Real numbers include all of these. It includes natural numbers, whole numbers, integers, and rational numbers. But it also includes another set on top of that, which are irrational numbers. Okay? And irrational numbers include pi, e, phi, the square root of 2, the square root of 3, the square root of any number that's not a perfect square, cubed root of any number that's not a perfect cube, the fourth root of anything that's not a perfect fourth power. So, the square root of 2 is, if you put it into a calculator, it would be 1.41, and it doesn't repeat. The decimal does not repeat. It does not terminate. It just keeps going forever, and so it is irrational. So same with pi. We know pi is 3.14159, and then the numbers keep going on and on and on forever, and they never terminate, and they never repeat. There's no pattern to the decimal. E is another one. We will get to E for sure in Algebra 2, so we will be looking at E. E has some pretty interesting qualities, especially when you're looking at some of the functions that we're going to be getting to. Okay. Phi is the golden ratio, and it has its own number, the golden number, and that's what this phi is identifying, and the golden number is, again, an irrational number. So these are all the different real numbers. So natural numbers are real numbers, and they are whole numbers, and whole numbers are integers, and integers are rational, and rational numbers are real numbers. But it doesn't go the other way. Irrational numbers are not rational. So that's why it's a bigger circle for the reals, because it has all those numbers combined. And then I've got a separate circle here. This separate circle has some other types of numbers, if you will, in them. These numbers, however, are not real numbers. They're not in the real number set. They're outside of the real number set. And so they kind of deserve their own set. They're not in the reals, and the reals are not necessarily in them, if you will. Although some professors may say, well, you can write a real number in the form of an imaginary number, and that is technically true. We're going to get there later in this lesson. But for now, I like to think of real numbers and the non-real numbers as a totally different set of numbers that are separate and unable to be reconciled. They're just completely different numbers. So a way to think about it, I've put down a number line here, and here's 0, and off to the right are positive numbers, and to the left are negative numbers. So a natural number such as 1, 2, and 3 are all in the positives. You could write down any natural number on a number line, and if 0, let's say 0 is the date, and let's say 0 is today. Today is time 0. Then any natural number you write down, you could identify how many years in the future it would take to get there. So if we were to write the number 3, if I were to write the number 3 down, we would be able to say, okay, it would take 3 years to get there from now. Again, whole number is 0, and we would say it would take no time to get there. We are there right now. This is the here and now. So that's the whole number 0, and we've already discussed naturals. So the special qualities of integers, which are negatives, we could say, okay, -2. I could write -2 down. If I write down -2, that was 2 years ago. We're talking about 2 years ago. If we wanted to use a fraction, and we wanted to say 2/3, we'd say, okay, that's 2/3 of a year from now. So it makes sense. Pi is 3.14159 ... It goes on forever. We can identify that it would take 3.14159 ... that much time to get there. Three and a little more years to get to that number. So these are all numbers that we could identify. They're attainable. We can see into the future to that. We can imagine what it takes to get there. We have a solid grasp of these numbers. These numbers down here, we don't have a solid grasp of. So let's just go through real quick. We've got infinity. Infinity is a number that's so far to the right that although we understand that it's forever ahead of 0, we can't really imagine how much time it would take to get there. In fact, it would be outside of our understanding, because you go as far as you can imagine into the future, and you're still not to infinity yet. You're not even halfway there. You're not even a fraction of the way there. It doesn't even appear as any more than a little blip in time if you wanted to get from right now to an infinity from now time. Okay? So I think that makes sense. Then we've got infinitesimals. So we've got infinity, infinite numbers, and then here we've got infinitesimals. These are outside of the real numbers. We've got infinitesimals. Infinitesimals are infinitely tiny. Infinitely tiny. There are mathematicians out there that claim that infinitesimals do not exist, and that an infinitesimal is really just 0. However, there are mathematicians that use infinitesimals to prove some quite interesting math theories. They're able to use them to do a lot of interesting things, and I've read some theses over the idea of infinitesimals and game theory, and it actually has some role to play. So they seem to actually exist, if you will. Infinitesimals do exist, however, they do not exist in the real numbers. I've represented it as 0.0 with a bar. So think of an infinite number of repeating zeros, and then after that infinite number of repeating zeros, there happens to be a 1 after it. Well, that's kind of silly to think about, but that's how I think of it. Another way of looking at it would be 1 divided by infinity. 1 over infinity. So if we were to look at the position just to the right of 0, that wouldn't be 1 over a billion. That wouldn't be 1 over a trillion. Remember, a billion or a trillion is just a small speck of a movement compared to infinity. Infinity is forever. So 1 over infinity would be an infinitely small movement, or 0.0 with a bar 1 would be an infinitely small movement, and that number would look like 0 if we were to put it on the graph here. It would still look like 0 to us. So that wouldn't necessarily mean anything to us. We would just say, in the real number sense, we would say we're still just talking about 0. So these are kind of weird, and I apologize for the weirdness, but they deserve their own little bubbles, I think. And then the last one, the one that we're really focusing on today, is imaginary numbers represented with the letter I. Imaginary numbers, we use the letter I. We use a lowercase I all the time. We don't use a capital I ever to represent imaginary numbers. And the square root of -1 equals I. In math, we have designed a formula for writing down any number with I in it. And we can write every number that has the letter I in it as A plus BI, where A and B are real numbers, and I is imaginary. So I think that's kind of neat. It's interesting, but let's just talk about I for a moment here. Can we put I, the imaginary square root of -1, into the number line? And I think we can prove it pretty quickly that the square root of -1 is not a real number. We can't simplify this into a real, rational, integer, whole number, or natural number. And we're gonna skip looking at that yet. We're gonna look at another number first, one that we might recognize a little easier. The square root of 4 we know is 2. 2 times 2 is 4. And the square root of a number is just asking the question, what number times itself equals this number inside of the square root? That's how you figure out what a square root of a number is. What number times itself equals -4? So I'll let you think about that for a moment. You can pause the video and try it out if you want. What number times itself equals -4? See if you can come up with a few different answers or a few different guesses. I think that's always awesome. Okay, hopefully you've come up with some thoughts. And don't worry about it. If you're wrong, that's okay. It's great to think of different ideas and then prove them right or prove them wrong. So that's the idea. So I would think a lot of people, when they see this right off the bat, they might think of the number 2. And so we say, okay, is 2 the answer to the square root of negative 4? Well, 2 times 2 is 4, not negative 4. So we could say right off the bat, absolutely not. 2 times 2 is not negative 4. It never has been. Remember, they have to be the same numbers as what number times itself equals negative 4. So then we go, okay, how about the square root of negative 4? Does that equal negative 2? Hopefully you thought of that number. That just kind of popped into your head as well. That's great. Negative 2 times negative 2. Uh-oh, a negative times a negative is a positive. So negative 2 times negative 2 is positive 4. So again, that is not true. You say, okay, I see that. How about 2 times negative 2? Yes, but 2 and negative 2 are not the same number. Remember, a square root asks the question, what number times itself, not what number times its opposite equals that number. The only thing that we can say about the square root of negative 4 that makes any real sense, because it is simplifiable. It's simplifiable, but it doesn't simplify down to a real number. And we need to know some of the rules of square roots to make some sense of this. But the square root of negative 4 is the square root of negative 1 times the square root of 4. We can break these up because a negative 4 is really the same as negative 1 times 4. Negative 1 times 4. So we can break this up into this grouping. So, can we simplify it any further? Well, absolutely. The square root of negative 1 times, and we know what the square root of 4 is. We've already discussed it. The square root of 4 is 2. So we get the square root of negative 1 times 2. And so we could rewrite this as 2i. 2i. 2i is definitely a number inside of this bubble. It lives here. It's a plus bi. Well, b is 2 in this case, 2i's. A is 0. 0 plus 2i. 0 plus 2i. So 0 plus 2i is one of the many numbers inside of this circle. And that's the same as the square root of negative 4. The square root of negative 4 can be written as 0 plus 2i. Okay? So now back to our technically simpler question, but I think the square root of negative 4 is a great one to look at first, because it's just, I think it makes more sense just looking at it. But back to the square root of negative 1. Again, we could guess that the answer is 1. 1 times 1 is 1, not negative 1. So then you say, okay, how about negative 1? Negative 1 times negative 1. Well, a negative times a negative is a positive, so again, that can't be it. And so we start to realize that the square root of negative 1 is not a number on the number line. It is not any of these numbers. The only thing we can say about it is that it's I. And I we already have inside the circle. Okay? So I had said earlier that you could technically put a real number into this circle here, and it depends on the mathematician how you want to look at it, but a plus bi is pretty open. So let's say we wanted to just use the number 2, and we want to write that as an imaginary number. You say, well, that's silly, it's not imaginary. You're absolutely right, it's not. It's a real number, but it could be put into the form of an imaginary number. We could write it as 2, that's the a. A is a real number. Remember, A and B are both reals. Plus 0. 0i. Well, if there's no i's, there's no imaginary, and it's a real number. It's a real number too. So 2 plus 0i, you can write it in here. However, I think it's a little bit cheating in the sense that it's not really an imaginary number. It's just been put into the form a plus bi. So I think you just want to be careful the way in which you think about it. Don't think of real numbers as imaginary numbers. Don't think of imaginary numbers as real numbers. But you can put any real number, any of these numbers. We could have used pi and written pi as pi plus 0i. So you could write any real number as an imaginary, but that imaginary doesn't exist, so it's 0 i's. So hopefully that makes sense. That was really just an overview of different numbers, hopefully to make imaginary numbers make a lot of sense. Let's go real quick back over what we've got here. We've got natural numbers. Use the capital letter N for natural numbers. Whole numbers, we use the letter W. Z for integers. Q for rationals. R for reals. They're all capital and they're script letters, so they have a special extra squiggle in them. Outside of the real numbers exist other numbers, which we talked about. Infinitesimals, these are infinitely tiny numbers. Infinite numbers, so infinity. And imaginary numbers, the number I. And let's move on. So let's see if we can understand imaginary numbers even better. So let's go back to our real number line. We've got 0 here in the middle, and then we've got positives over here, all positive real numbers. That can be 1, 2, 3, 10, 50, 1/5, 2,000 divided by 60. These are all numbers that exist in the positive reals, and then we've got all the negative real numbers. And we can reconcile our real numbers with imaginary numbers in the sense that we can have a number line going vertically, and we could have positive imaginary numbers and negative imaginary numbers, and they cross here. So you can think about it that way. So then a number, say right here, you say, okay, how can you reconcile it? Well, it's easy. Here I is 0, so we've got 3 plus 0i. Lives right there on this xy axis. Although it's not really an xy, it's an x imaginary y axis, if you will. So we could do it like that, xi. So then 3 plus 0i lives there. I'm going to get rid of these so they're not confusing us. I think we get the picture though. Right? So positive i's up there, negative i's down there. We've got x, positive and negative. So 3 plus 0i lives there. You say, okay, well then what might live right there? Ooh. Looks like it's right maybe 2. Because it's down 2 minus let's say 2.5 i's. So 2 minus 2.5i. Starting to see the picture here? Alright. Let's go ahead and look at a number way over here. So this number is negative in the x direction and negative in the I direction. So let's see here. We could say this is negative 71/6. Why not? Minus, so it was left 71/6. I just made that up. but it's a reasonable made-up number. And it's down maybe not quite as far as this guy. So maybe this is 2 minus 2i. And there you go. This would be an imaginary axis. Let's do one right here. Notice in the x-axis direction, in the horizontal direction, we have gone 0 right and 0 left. So we know that a is 0 plus bi. B being how far up we went. Looks like we went up 3. So 3i. 0 plus 3i. Which could be simplified, of course, to just 3i. This could be simplified to just the number 3. Okay. And then we've got numbers over here. Looks like we went left, let's say 4. So negative 4 plus, because we went up in the I direction. So negative 4 plus 2.7i. Okay. We can put a number right so here. This could be going up 3.1415. Oh, pi. Up pi, and we went right pi plus pi I. Pi plus pi I. So hopefully this is making sense. Any real number and any imaginary number, and you can combine them, and we could actually literally use an xi axis to represent any imaginary number. We would just represent a whole bunch of different random imaginary numbers. Of course, we did small numbers. We didn't do anything outrageously huge, but we could add these. We could subtract them. We could multiply them together. We could divide them from each other. You could do all kinds of fun stuff with them. You can combine them. They are compatible numbers, if you will. Right? So let's take a couple of simple numbers here. So let's go ahead and look at this number here and this number here. So let's go ahead and add these two numbers together and see what we get. So we're going to take a moment to add a couple of imaginary numbers. These are definitely imaginary numbers. I'm going to add them together and see what we get. So we're going to go ahead and do that off to the side here. So we've got negative 4 plus 2.7i plus, so we're adding 2 minus 2.5i. I don't know what I'm doing there. 0.5i. And we're adding them together, so I got my plus sign there. And remember, these are incompatible numbers. Just keep that in mind. An imaginary number and a real number cannot combine. But two real numbers definitely can be combined. So negative 4 plus 2, negative 4. Add 2 to negative 4, and that makes negative 4 get smaller to negative 2. And then 2.7i plus negative 2.5i. Now, plus a negative is the same as a minus. We can drop that plus sign altogether. So 2.7i minus 2.5. 2.7 minus 2.5 is 0.2 plus 0.2i. And we get a number. Negative 2 plus 0.2i. Can we add these together? Well, the first thing we would want to do, if we were saying, okay, these are two separate numbers and we want to add them together, we'd want to get them into the same form. And that form is always a plus bi. So can we rewrite 3 as a plus bi? Absolutely. 3 plus 0i. Can we write 2i as an a plus bi? Absolutely. 0 plus 2i. And then we can add them together. 3 plus 0 is 3, and 0 plus 2 is 2, and 3 plus 2i, well, that's what we started with. So no change. That is the number. Okay. Hopefully that's making sense. If not, you can rewind and rewatch. Say we're given something like this. We've got 4 plus 7i plus 6. Can we combine like terms? Absolutely. And we can actually convert 6 into a plus bi by just going plus 0i. We just add that in there. And then add vertically. So 4 plus 6 is 10. 7 plus 0 is 7. And we're done. 10 plus 7i would be the answer. These are pretty simple, but I just want us to not get confused by the simpler problems. The simpler the problem, sometimes the more it deviates from what you're normally looking at, which is this a plus bi. So we can add these together, or in this case subtract them. We need to be careful though. So we want to look 6 minus 8. 6 minus 8. 6 minus 8. So we're taking 6 away from a negative 8 to get a negative 2. You're saying, wait a second, that's not the number I got. Think about it as positive numbers are numbers that you have earned of money. So we've earned $6, and negative numbers are what we owe. We owe someone $8. So if you earned 6 and you owed $8, if you try to reconcile with the person that you owed money to, you would still owe them $2 more. You had 6, you owed 8, you gave them the money that you owed that you could, and you still owe them $2. 7, this is 7i, 7i minus negative 4i. Minus a negative. Two negatives make a positive. So we've got 7i plus 4i. Right? Minus minus makes a plus. So 7 plus 4 is 11. A little bit more complicated there, but totally doable. So mathematicians are not above trying to confuse you, and this is confusing. These numbers have been swapped. This is not in the form a plus bi. This is in the form di plus a, and the second number is. So to get it into the right form, we would just need to swap the numbers before we move forward. So we could rewrite it as 3 plus 4i. Or you could just kind of keep in mind that 11 and 3 are not i's, so we can combine them. So what is negative 11 minus 3? Negative 11 minus 3 would be negative 14. So we've got two negatives that we're adding together, and it makes a bigger negative. Okay? Negative 11 minus 3. So you owed $11, and then you owe 3 more. You didn't earn anything. You just owed, in both cases, you owed 11 and then you owed 3 more. That's owing $14. Negative 2 i's minus 4 i's. So negative 2 minus 4, again you owed $2 and then you owe 4 more. That means you owe 6. So negative 6i. And notice we didn't even have to swap them. Now if you say that's just so confusing, then rewrite it. Rewrite it on another sheet of paper. Rewrite it as 3 plus 4i. Just swap them. Don't keep the I in that position. You're swapping the whole entire 3 and the entire 4i. They just swap positions. And now you've got it in the right form. Now you've got negative 11 minus 3 still gives us negative 14. And negative 2 minus 4 gives us the negative 6i. So, hopefully that makes sense. This would be an appropriate answer. We could multiply these two numbers together to get a new number. And is that number going to be imaginary? Do two imaginary numbers being multiplied together give us a new imaginary number? I think we need to identify that, generally speaking, that will be true. This will make a new imaginary number. So this is kind of like that factoring stuff that you did in Algebra 1. That was a while ago, I admit. So we're going to do 2 times 3. And so that's, if you want to remember the FOIL method's very helpful. FOIL is first, outside, inside, last. It's just a method of multiplying two binomials together. So we're going to take the first term in the first parentheses and the first term in the second parentheses. That's where the F comes from in FOIL. First. So the first two terms. 2 and 3. 2 times 3 is 6. We're just multiplying them together. Outside. O is for outside. Outside, this means furthest apart. The two furthest apart numbers are the outside numbers. So first outside. Outside is here, outside. I'm going to bring that 6 down. It's a little high. It's going to get in our way. Alright. Outside numbers, that's 2 times negative 7i. Now remember I said that you cannot add a real number and an imaginary number together. You can't add these two numbers, but you can multiply them. Because there is a real number here too, and a real number 7 attached to the I. So you can multiply the real numbers together. So 2 times 7 is 14. It's actually 2 times negative 7, which would make us a negative 14. And there's still an I attached. That I comes with it. So we have negative 14i. So that's the O in FOIL. Inside is the I in FOIL. Inside. Inside meaning the inner or closest numbers. Insides. These are the insides. And so we're going to multiply those together, and we have 4i times 3. 4i times 3. They're both positive numbers, positive 4 and a positive 3. So we're going to get a positive number. So plus, positive times a positive is a positive. 4 times 3 is 12. And we've got an I there, so we get 12i. Okay? So the last is L in FOIL. The last number in the first group and the last number in the second group. So that's where the lasts come from. So it's first, outside, inside, last. So the lasts are multiplied together last. 4i times negative 7i. So 4 times negative 7, well, that's going to give us a negative. A positive times a negative is a negative. So we're getting a negative here. And 4 times 7, 28. And I times I. I times I. Well, x times x would be x squared. I times I would be I squared. So we're getting I squared here. And there we go. We could stop there and say, yep, this is the number. And that's true. But it's simplifiable, so we do need to keep going. It is necessary to keep going. So let's go ahead and finish it up. The two middle terms, if we used FOIL to multiply the binomials together, if we used FOIL, then we should be able to just add these two numbers together. So negative 14 plus 12. Negative 14 plus 12 is negative 2, so we get a negative 2i. We're going to just bring that 6 down, because we didn't do anything to the 6. And we're going to simplify this. So this is a concept that we haven't really thought about before. But what is I squared? Well, we know that I equals the square root of negative 1. We know that I equals the square root of negative 1. We know that I squared then should equal the square root of negative 1 squared. A square root and a square cancel each other out. If a square root and a square cancel each other out, then what's inside is what's remaining. So the square root of negative 1 squared is just negative 1. So we could rewrite this as negative 28 times negative 1, which is a real number. I squared is a real number. That's interesting. Okay, 6 plus 28. That's what we're going to do next. But let's go ahead and look at this. So negative 28 times negative 1, a negative times a negative is a positive 28. Positive 28. Six plus 28, 34. Oh my goodness. You go, wow, what is going on here? It's interesting. An imaginary number, a plus bi form, times another imaginary number in a plus bi form, equals an imaginary number in the a plus bi form. Crazy, but true. An imaginary number times another imaginary number equals an imaginary number. You say, no, I don't believe you. Doesn't make sense. And you know what? I'd say good. I'm glad you're thinking that, because didn't we say I squared equals a real number? And the answer is yes. So not always does an imaginary number times an imaginary number equal an imaginary number. Sometimes an imaginary number times another imaginary number will equal a real number. We prove it right here. I times I, two imaginary numbers, equals a real number. So in this case, it equaled an imaginary number. Okay. So we've got two imaginary numbers. These are definitely imaginary. This is I times I. So we could use FOIL. It's unnecessary because this is simplifiable down to just I, and this is simplifiable down to just I. But let's do the FOIL method for our own sake so that we see what's going on. So 0 times 0 is 0 plus 0 times I would be 0i. Okay? Inside plus 0i, and then lasts I times I, or 1i times 1i, which would just be I squared. 0 plus 0 plus 0 are zeros, plus I squared is just I squared. And there we go, we get our I squared. And then we can rewrite this as the square root of negative 1 squared. Square root and a square cancel each other out, we're left with negative 1. So I squared equals negative 1, which is our answer. So you say, okay, maybe I see a pattern here. If you're multiplying two imaginary numbers that are the same, then we'll always get a real number. And I think we're onto something here. Now again, it's just the first binomial is the same as the second binomial. So we're just multiplying them together. So this actually could be rewritten as 3 plus 4i squared. But we can break that up into two binomials and then use the FOIL method to multiply them together. So first, 3 times 3 is 9. Outside, 12 i's. Inside, 4 times 3 is 12 i's. And then lasts, 4i times 4i. This isn't looking good. This is looking bad for us. It looks like this isn't going to be an imaginary number. So if you were thinking two of the same binomials multiplied together will give us a real number, it's not necessarily looking good. 12i plus 12i. 24i. Uh-oh. I don't think there's any way to get rid of that. So I think we're stuck with an imaginary number here. 16i squared. Well, we should have that down now. It's just negative 16. Right? I squared becomes negative 1. Negative 1 times 16 is negative 16. Add that to the 9. So combine those like terms, and we're going to get negative 7. So negative 7 plus 24i. That is definitely an imaginary number. So you go, okay, is there a pattern to multiplying two imaginary numbers to get a real number? And the answer is yes. So let's go ahead and do a little bit of a tweak to this problem. We're going to use the same problem, but we're going to change it just a tiny, tiny bit. It's no longer squared. Instead, what it is what's called conjugate pairs. You probably remember conjugate pairs. You just change one of the binomials into a opposite sign. So we have a plus and a minus. So 3 plus 4i, 3 minus 4i. This is going to get us a real number. We could plug any one number in for the 3, any one number in for the 4, as long as it's a plus bi, a minus bi, where the a's are the same and the b's are the same, we will get a real number. So I'm guaranteeing us to get a real number this time. So first, 3 times 3 is 9. Outside, minus 12i. Inside, plus 12i. Last, minus 16i squared. Okay. Combine like terms, start with the middle. Negative 12i plus 12i. You owed somebody $12 and then you give them $12, you owe them nothing. You have nothing. 0. This just goes to 0. 0i. So we've got 9 plus 0i minus 16 times a negative 1. I squared is negative 1. A negative times a negative is a positive, so we can combine these to become a positive 16. The 0i just goes away, so we're left with 9. 9 plus 16 is 25. So our answer is 25. If you want to write it in a plus bi form, 25 plus 0i is appropriate, but it is a real number because it can be written as just 25. If you've got two conjugate pairs in the form of a plus bi, you're always going to get a real number as your output. I think this was the most fun thing that I learned in Algebra 2 when I first saw this. I thought it was just so neat. So it's pretty fun. But I think we've already seen a little bit of it. So we're going to just kind of build upon it. And that is, what does I equal? It's the square root of negative 1. We know that. I squared is the square root of negative 1 squared, which we already have identified as negative 1. It's a real number. I cubed is the square root of negative 1 cubed, which could be rewritten as the square root of negative 1 squared times the square root of negative 1 cubed, right to 3. There's 3 of them. There's 2 of these, that's the square, and then a third one there. So square root of negative 1 times the square root of negative 1 makes the square root of negative 1 squared times the square root of negative 1. Well, we already know that a square root and a square cancel each other out. So we're left with negative 1 times the square root of negative 1. Whoa. We can simplify this to just negative square root of negative 1. Well, we know that the square root of negative 1 is I, so we could just rewrite this as negative I. So we're going to do a little bit of simplification here just so that it's not quite so messy. I just walking through the steps here. You can write them down. Go ahead and pause the video and write these steps down, but I'm going to make it simpler here. I don't want it so messy here. So we've got I squared, which is negative 1, I cubed, which is negative I to the 4th. I to the 4th. Well, we know it's the square root of negative 1 squared times the square root of negative 1 squared. And so squared times squared would be to the 4th. This is to the 4th power. So this is I to the 4th. But we know that this is negative 1 and this is negative 1. So we can rewrite this as negative 1 times negative 1. And we know a negative times a negative is a positive 1. That's a real number. So I to the 4th is just 1. So again, you can write down these steps, and then maybe pause the video so you can write those down. And then I'm going to simplify it. So I to the 4th is just 1. So then you say, okay, where are we going here? I to the 5th. We're going to start seeing a pattern here. This is a pattern, and that's what made me so excited when I first saw this. Is that this is a pattern, a circular pattern that's repeating. So I to the 5th. I to the 5th is I to the 4th times I. What is I to the 4th? It's just 1. 1 times I. That's just I. I to the 5th is I. So if I to the 5th is I, what is I to the 6th? Well, I to the 6th is just I to the 4th times I squared. And I to the 4th is just 1. 1 times I squared. Well, we know I squared is negative 1. So I to the 6th is negative 1. Again, I'm going to simplify it down, so if you want to write these notes down, go ahead and do that. But I'm going to just rewrite it. I, negative 1, negative I, 1, I, negative 1. What do we think the next one's going to be? I to the 7th. We could rewrite this just to make it even more simple. We got I, negative 1, negative I, 1, I, negative 1. It's repeating, so we should guess that it is going to be negative I next. Well, we know that I to the 4th is just 1. We know that I cubed is just negative I. Yes, indeed. I to the 8th. Well, that should just be 1, because that is I to the 4th times I to the 4th. Makes I to the 8th. And we know that I to the 4th is 1, I to the 4th is 1, 1 times 1 is 1. So again, we can erase, simplify down, and just write the end answers. So, I am making up a number. It doesn't matter what number. I'm going to make it big though. I to the 573rd. I can figure this out, and so can you. If you want to give it a shot, go ahead and pause the video and give it a shot. See if you can figure out the pattern. With this knowledge here, we can figure this out. Because it's just a pattern. We just take our number, divide it by 4. How many times does 4 go into 5? Once. Drop 4 down, subtract, get 1. Bring the 7 down. Just long dividing. How many times does 4 go into 17? Well, we should come up with the answer of 4. 4 times 4 is 16. Subtract. We get another 1. Bring the 3 down. How many times does 4 go into 13? We should come up with the answer of 3. 3 times 4 is 12. And we get another 1. That was just coincidence that we got 1 every time, but we did. As our remainder. So 1 is our remainder. That's the only thing that really matters. Everything else here is silly. 143 remainder of 1. 143 R1. We're going to write that down. 143 R1. So that's, we got, when we divided 573 by 4, we got 143 with a remainder of 1. We'll do it. Raised to the power of 1. Okay. So, I to the 4th raised to the power of 143 equals I to the 572. Because there was 1 remaining. I to the 1st. I to the 4th is just 1. 1 raised to any power. 1 raised to any power is just 1. And I to the 1st is just I. So I to the 573 is just I. So as long as you divide by 4 and then figure out what your remainder is, if that remainder was 1, then the answer is I. If the remainder is 2, then the answer is negative 1. If the remainder is 3, then the answer is negative I. And if the answer is 4, then your answer is 1. Simple. Do we need to see that one more time? Let's go ahead and do one more. I think these are pretty fun though. I to the 764th. This is an even, so the answer is either going to be negative 1 or 1. If it was odd, it would be I or negative I. Those are our choices. So we know it's an even number. Our answer is going to be either negative 1 or positive 1. We just need to figure out which one it is. It's a 50-50 shot right now. We want to know exactly which one it is. So we're going to divide 764 by 4. We know 4 divided by 764. 4 goes into 7 once with a remainder of 3. Drop the 6 down. 4 goes into 36 9 times. Here this is 0. Drop the 4 down. And then 4 goes into 4 once. And we get a remainder of 0. So if we get a remainder of 0, then we know that this is I to the 4th raised to the power of 191 times I to the 0. There's no remainder. And so we can rewrite this as 1 to the 191st times 1, because I to the 0. Anything to the 0th power is just 1. So we just get 1. And then 1 to the 191st power is still just 1 times 1, which is you might want to write this down. So if you get a remainder of 0, then it's 1. If it's a remainder of 1, it's I. If you get a remainder of 2, it's -1. And if you get a remainder of 3, it's -I. So that's pretty neat. It's kind of fun. So you could do I to any power. In the thousands, in the 10,000, it doesn't really matter. As long as you know how to long divide by 4, you can get your solution. And you don't even have to do all this work. You just note, okay, I got a remainder of 0. Done, it's 1. I got a remainder of 1. It's I. I get a remainder of 2. It's -1. I get a remainder of 3. It's -I. Done. It's that simple. Okay. So I think you're ready for the assignment. If you have any questions, please Canvas message me. That's the best way to get a hold of me. Of course, you can email me as well. I do try to check my emails every day, but I do check my Canvas messages probably a little bit more often, so I would recommend you look at those. Whenever I get a free chance, I look at my Canvas messages. So please get a hold of me if you've got any questions. Also, I'm going to hound it home. You should go ahead and talk to some friends that you have in class and see if you can get their contact information, either email or phone number or both, so that you can contact them. If you have questions, you can talk with them. Maybe they have the same questions, maybe you can talk it through together, and maybe it'll make more sense. I can't say it enough that working together will help solidify and confirm your beliefs and your understanding of math. So work together. Don't be afraid to get a partner from class that you can work with, even if it's remotely.